Hello everybody, welcome back. Today we're going to start talking about asymptotic notation. So here we're going to sort of just introduce this whole idea of asymptotic notation and describe some of the advantages of using it. So last time we ran into this really interesting problem that computing runtimes is hard, in that if you really want to know how long a particular program will take to run on a particular computer, it's a huge mess. It depends on knowing all kinds of fine details about how the program works, and all kinds of fine details about how the computer works, how fast it is, what kind of system architecture it is. It's a huge mess. And we don't want to go through this huge mess every single time we try to analyze an algorithm. So we need something that's, maybe a little bit less precise, but much easier to work with. And we're going to talk about the basic idea behind that. And the basic idea is the following: that, there are lots of factors that have an effect on the final runtime, but most of them will only change the runtimes by a constant. If you're running on a computer that's 100 times faster, it will take 1/100th of the time, a constant multiple. If your system architecture has multiplications that take 3 times as long as additions, then if your program is heavy on multiplications instead of additions, it might take 3 times as long, but it's only a factor of 3. If your memory hierarchy is arranged in a different way, you might have to do disk lookups instead of RAM lookups, and those will be a lot slower, but only by a constant multiple. So the key idea is, if we come up with a measure of runtime complexity that ignores all of these constant multiples, where running in time, n, and running in time 100 times n are sort of considered to be the same thing, then we don't have to worry about all of these little bitty details that affect runtime. Of course, there's a problem with this idea if you look at it sort of by itself, that if you have runtimes of 1 second or 1 hour or 1 year, these only differ by constant multiples. A year is just something like 30 million seconds, and so if you don't care about factors of 30 million, you can't tell the difference between a runtime of a second and a runtime of a year. How do we get around this problem? Well, there's a sort of weird solution to this. We're not going to actually consider the runtimes of our programs on any particular input. We're going to look at what are known as asymptotic runtimes. These ask, how does the runtime scale with input size? As the input size n gets larger, does the output scale proportional to n? Maybe proportional to n squared? Is it exponential in n? All of these things are different. And in fact, they're sort of so different that as long as n is sufficiently large, the difference between n runtime and n squared runtime is going to be worse than any constant multiple. If you've got a constant multiple of 1,000 n, might be pretty bad with that big number in front, but when n becomes big, it's still better than n squared. And so by sort of only caring about what happens in this sort of long scale behavior, we will be able to do this without seeing these constants, without having to care about these details. And in fact, this sort of asymptotic large-scale behavior is actually what you care about a lot of the time, because you really want to know what happens when I run my program on very large inputs. And these different sorts of scalings do make a very large difference on that. So suppose that we have an algorithm whose runtime is roughly proportional to n, and we want to say we run it on a machine that runs at about 1 gigahertz. How large an input can we handle such that we will finish the computation in a second? Well, if it runs in about size n, you can handle about 1 billion sized inputs before it takes more than a second. If instead of n, it's n log n, it's a little bit slower. You can only handle inputs of size about 30 million. If it runs like n squared, it's a lot worse. You can only handle inputs of size about 30,000 before it starts taking more than a second. If the inputs are of size 2 to the n, it's incredibly bad. You can only handle inputs of size about 30 in a second. Inputs of size 50 already take 2 weeks. Inputs of size 100 you'll never ever finish. And so the difference between n and n squared and 2 to the n is actually